You ever been in one of those new cars with the fancy cruise control and it just slams on the brakes for absolutely no reason? It's pretty startling, right? And it gets you thinking about this weird paradox. The smarter our cars get, the stranger their mistakes seem to be. And we're not talking about broken parts or software bugs here. No, this is something way more fundamental. So that's the big question, isn't it? If the hardware is flawless and the code is bug-free, why do these cars still make these, potentially dangerous mistakes? Well, the answer isn't that something is malfunctioning. It's a much deeper, more interesting challenge. And it actually has a name.
And that name is SOTIF. It stands for Safety of the Intended Functionality. Okay, it's a bit of a mouthful, I know, but the idea behind it is pretty straightforward. SOTIF is all about the hazards that pop up even when a system is doing exactly what it was designed to do. See, it's not about the car braking. It's about the design itself having a kind of blind spot when it bumps up against the messy, unpredictable real world.
So let's start with the kind of tech that many of us are already using every day. We're talking levels 1 and 2 automation. These are really just driver aids, systems where you, the human, are still very much the co-pilot, and you're always responsible for watching the road. But even here, these SOTIF issues can be, well, pretty alarming. This brings us to a classic SOTIF problem, something called ghost braking. So picture this. You're cruising down the highway, adaptive cruise control is on, everything's great. You start to go under a big metal bridge and bam, the car slams on the brakes because it thinks that bridge is a giant truck stopped right in your lane. So what on earth is actually going on there?
Well, the culprit is actually a physical limitation of the radar sensor itself. You see, automotive radar is fantastic at measuring distance and speed, but it has really poor vertical resolution. That means it can't easily tell the difference in height between a bridge that's, say, 20 feet above you and the back of a truck trailer that's right in front of you. As far as the radar is concerned, they're both just big metallic objects in the exact same spot.
So the fix isn't just about getting a better radar, it's about thinking smarter. Engineers are always developing better algorithms that can learn to recognize the signature of things like bridges and signs. But the real game changer here is a concept called sensor fusion. This is where the system takes the radar's data and combines it with images from a camera. So if the radar is screaming stop, but the camera is saying, hey, the road is totally clear, the system can correctly identify it as a ghost and just ignore the false alarm. Okay, now let's step it up to level 2. Here, the problem gets a bit more complex because now the car is controlling both your steering and your speed. So imagine you're in an exit lane. You're following another car. Your cruise control is set to 70 miles per hour, but you're only going 40 because of the car ahead. Then that car exits the lane. All of a sudden, your car has lost its target. What does it do? It floors it. It tries to rocket back up to 70, even though your lane is about to end. The solutions for this are actually pretty clever. First, there's something called a hysteresis algorithm. This basically gives the car a little bit of short-term memory. It remembers the car that just left for a few seconds, which prevents that sudden jarring acceleration. Second, and this is just as important, engineers simply limit the car's acceleration authority. They put a leash on it, preventing it from ever speeding up in a way that would feel uncomfortable or unsafe to a person. And now we come to level 3. And folks, this is a huge leap. The car is now driving itself under certain conditions, and you, the human, you're not the co-pilot anymore, you're the backup. You're actually allowed to take your eyes off the road. And this creates one of the single most difficult challenges in all of automation, the handover. You see, the whole relationship changes. At level 2, you are a driver. You have to constantly monitor everything. But at level 3, you become what they call a fallback-ready user. You can read a book, check your email, but you have to be ready to grab the wheel the instant the car asks you to. And believe me, that distinction is everything. And here's the SOTIF hazard that this creates. The car's cruising along doing its thing, but then it runs into something it wasn't designed for, like, say, dense fog that totally blinds its sensors. It immediately issues a takeover request, a tour, telling you, hey, it's your turn to drive. But what if you're totally engrossed in a movie and you just don't notice? The result is a car driving blind with no one at the controls. And the window you have to respond in? It is terrifyingly short. Research shows that a distracted person needs somewhere between 2.6 and 6 seconds just to switch off from what they were doing, figure out what's happening on the road, and then take effective control of the car. That is an incredibly brief amount of time to go from relaxing to making a potential life or death decision. So how does the car possibly get your attention in time? Well, it uses something called an escalation ladder. First, a visual alert will pop up on the screen, If you don't respond, you'll hear an auditory chime. Still nothing. The seat starts to vibrate. That's haptic feedback. And if all else fails, the final step is a kinesthetic jolt. The car will actually give a short, sharp tap of the brakes to physically get your attention.
But what if all of that fails? If you're completely unresponsive, the car has one last card to play: the minimum risk maneuver, or MRM. This is the system's ultimate failsafe. It has to perform some pre-planned action to get itself to a state of minimal risk. Now, depending on the situation, that could mean safely coming to a complete stop right there in its own lane, or ideally, finding a way to pull over to the shoulder.
All right, let's climb the ladder one more time, all the way up to level 4. At this point, the human is completely removed as a backup, at least within a defined area, like a specific part of a city. The car is totally on its own. It has to handle everything, which, as you can imagine, introduces a whole new class of SOTIF problems.
So the crucial issue here isn't just about what the car can see. It's about what it can't. So in this scenario, a robo-taxi is rolling up to an intersection, but there's a huge truck in the next lane completely blocking its view of the traffic light. The car's camera sees nothing, so it just assumes the way is clear, and it drives straight through a red light.
This is the problem of occlusion. A truly autonomous car can't just react to what's in its field of vision. It has to be smart enough to reason about its own blind spots. It has to understand that just because it can't see the traffic light, that doesn't mean it isn't there. It has to be programmed to assume that danger could be lurking in the unknown.
And this is where the solutions get really, really cool. The car starts using multiple sources of information and something called cooperative perception. First, its high-definition map tells it, hey, there should be a traffic light right here. Then V2X, which is vehicle-to-everything communication, allows the traffic light itself to broadcast its status, red, green, yellow, directly to the car. Finally, the car performs what's called rationalization. It compares all this data and concludes, my map and the V2X signal both say there's a red light, but my camera can't see it. Therefore, my camera must be blocked.
So after climbing this entire ladder of autonomy, from a simple cruise control all the way to a car that can reason about its own blind spots, we arrive at the final, biggest question of all. How do we actually prove that one of these incredibly complex systems is safe?
Well, the formal answer is a process called verification and validation, or V&V for short. And this is a massive, massive undertaking. We're talking millions of miles of simulated driving, thousands of hours on closed test tracks, and then finally, millions of miles on actual public roads, all to prove the system is acceptably safe. But that just raises a really important philosophical question. What does acceptably safe even mean?
And that brings us to this key concept: positive risk balance. Look, the goal isn't to create a car that can never, ever have an accident. That's probably impossible. The goal is to create a system where the safety benefits, like, eliminating all the accidents caused by drunk, distracted, or tired human drivers, massively outweigh the new, specific SOTIF risks that the automation itself introduces. It's not about being perfect. It's about being better. Which leaves us with one final, pretty provocative question. We know humans are flawed drivers. We get distracted, we get tired, we make dumb mistakes. If we can build a car that is statistically proven to be safer than the average human driver, is that safe enough for us to hand over the keys? That's something I think we're all going to have to decide.